Hey everyone, welcome back to the world of probability. This is Mrs. Fallon. We are on page 290 of your student journal. We are going to tackle today some different kinds of probability, independent, dependent, that kind of stuff. Again, you're going to need that handout, that extra notes packet thing that I was talking about in the last video. We're going to use that for every section here just because the examples here are a little bit wordy. And I figured that would give us a little bit less time on the video of having to write everything out. In addition, I think it would be good if you had a piece of paper or a part of your notebook or whatever, note card, something, where you're going to kind of organize all of your formulas for this unit. So it is going to be important that you're able to kind of find these formulas. And so if they're buried within your notes, that might not always be the best option. So what I did is I just kind of created just like a little note page, right? And I'm going to write down all of my different formulas on those note pages, or on that note page. So today we're gonna kind of start that page, and then we're gonna add to it as we go throughout the course of this unit. All right, let's go ahead and get started. Okay, so we're going to talk about something called independent and dependent events. So independent events are two events that are independent when the occurrence of one event does not affect the occurrence of the other. Okay, so here's what you kind of need to know. That was like the formal definition. So I guess how I would, paraphrase that, I would say when two events are not affected by each other. So what I mean by that is, let's say you roll a number cube, a die, right? So you roll a die and then you spin a spinner. Those two events, the event of you rolling a die and the event of you spinning a spinner, are what we call independent events. Because you rolling a die has nothing to do with the outcomes of you spinning the spinner. Now, if we said something like, okay, I'm going to pick a number out of a hat, for example, or maybe you're picking for a holiday celebration, or I don't know, whoever. And let's say you pick all names in a hat. Let's say you and your 5 friends, so there's 6 names in the hat, and you pick one. Well, the probability of you getting your best friend, for example, is different if, let's say, you picked second as opposed to first. Because if you pick second, then someone else had already gone before you, and therefore changed the number of like options that were available to you. So that's what we call dependent events. So I guess when two events are not affected by each other, and then dependent events when they are affected by each other. So I guess we don't really need to write that down, but that's kind of what they're getting at. And then we're going to talk about something called conditional probability, and there's a lovely formula for that. And so that's, I'm just going to write this down. The probability that event B, so we're going to label these kind of, A and B and that kind of stuff. The event B occurs given that event A has already happened. We'll just say has occurred. So what that means, there's a specific notation for that, and that is probability of B, and then there's a line, and then A. So what this means is the probability, you're going to see this notation. This means probability of B given A has happened. So what we're talking about here is, like, for example, if you were drawing a card out of let's say you're picking a random card out of a deck of 52. And let's say what's the probability of you getting a club? Well, okay, there's 13 clubs in a deck. But what's the probability of, okay, let's say you draw first and keep your card, and then your friend draws second. What's the probability that he or she gets a club? Well, he or she is dependent upon whatever you came up with, right? So if you got a club, that lowers the probability of you getting a club. Either way, you picked a card out of that deck, which means there are less values or less cards to choose from at the end. So that's what we mean by a conditional probability. All right. Trying to fix the lighting here. I notice it's a little bit bad there. Hopefully that is a little better. All right, so what I'm going to do now, I'm going to show you a couple different formulas. So we're going to talk through them, and then we're going to do some examples. So I'm going to grab this page. I'm just going to call it, I don't know, my formula page or whatever you want to call it. You don't even have to call it anything if you don't want to. I'm going to call it a real generic name called formula page. All right, so I'm going to start with my independent, if my two events are independent of each other. So remember, independent events are stuff like, rolling a die and spinning a spinner. One does not depend on the other. So what you're going to see is it's going to be written like this. Probability of A and B. What's the probability of rolling a 2 and spinning a red on your spinner? So when the two events are independent of each other, all we're really doing is multiplying them together. So the probability of rolling a 2 and spinning a red on the spinner, you would take each individual probability of that happening and multiply them together. So for a dependent event, it's a little bit different. Okay, so let me write this down. So again, it's the probability of both things happening, right? So probability of A and B. So what it looks like is the probability of A happening times the probability of B given A has already occurred. So there's that notation again. So what this is implying is that, again, let's say we take the scenario of, drawing names or picking a number out of a hat or whatever. So the probability of A, let's say there are 5 numbers in a hat. It's 1 out of 5, right? The probability of B happening given A. So the probability of picking a 1 given that somebody has already, chosen a card or chosen a number. So what this means is it's going to change the number of outcomes in the event that we're talking about. It could change, again, if we're looking at clubs or something, someone else could have already picked a club. And so therefore it could change the total number of favorable outcomes that are available. So anyway, this is what this means is that A has to have already occurred. So that's what we mean by a dependent event. And the last one we're going to add on our sheet today, but we're going to continue to add as we go along throughout this unit, conditional probability. All right, so conditional probability is a little bit more, complicated. So it's a ratio. It's the probability of A and B happening. So again, that's kind of this whole scenario up here. So what we're saying here is the probability of A and B happening over the probability of A occurring. So again, depending on the situation, we would then use that to kind of help us figure out the likelihood of a certain event happening. All right, so like I said, this is kind of our formula page. We're going to continue to add through it or add to it as we go along. What I would encourage you to do is just, like I said, keep it handy. I kind of refer back to this because I don't even have all these formulas memorized. So it's helpful to have them all in one spot. All right, so kind of put that to the side. And then let's grab your that extra notes packet that I was talking about. Where did I put it? And we are going to take a look at the bottom of page 2 where it says 10.2. So this is where we're going to start, okay? So we'll start with kind of talking about some of these examples and using the independent, dependent, and all that kind of good stuff. All right, so let's get to it. All right, so we're on the bottom of page 2. We're talking about, here's a situation. So we have a bag contains 6 pieces of paper, numbered 1 through 6, okay? A student randomly selects a piece of paper, replaces it, and then randomly selects another piece of paper. Use a sample space, so there's the vocab from the first unit, or first section, to determine whether randomly selecting a 5 first and then randomly selecting an odd number second are independent events. All right, so what we're getting at here is, first of all, when they say a sample space, it means for us to kind of write out all of the outcomes. So it says a bag contains 6 pieces of paper. So we have 1, 2, 3, 4, 5, 6. So our sample space is really just those 6 pieces of paper. And so what we want to know is the randomly selected, they replace it. So this is kind of some keywords here. If they didn't replace it, then this would, this is going to kind of change something from an independent to a dependent event, not to spoil the outcome here. But Anytime you replace this, in other words, you're not gonna then change. So like when I like choose and pick a number out of a hat here or pick a number out of this, I have an equal probability of hitting a 1, 2, 3, 4, 5, or 6. The second person who chooses, right, because I replaced my number, has the same probability as I do, right? Because they have the same chance of getting a 1, 2, 3, 4, 5, 6. If I held on to my piece of paper, that's when that second probability changes. So that's the difference between kind of like an independent and a dependent event. A dependent event means that you changed the outcomes, the total. You didn't replace the piece of paper, whatever the scenario is. So the replaces it is a really key word to represent independent relationships. But let's continue on. So it says, use the sample space to determine whether the randomly selecting a 5 first and randomly selecting an odd number second are independent events. So what they're trying to show is the probability of 5 is like 1/6, right? Because the probability of getting a 5 is 1/6. The probability of getting an odd number, well, there are 1, 2, 3 odd numbers out of 6, which is 1/2. So if it were an independent event, so let's go back to our formulas, right? If an independent event, we would just multiply them together. So if I multiply those together, I would get 1/6 times 1/2 equals 1/12. If it was a dependent event, I would get a different value, right? So let's say the probability, so a dependent event means I take the probability of A happening, but times by the probability of B given A has already occurred. So the probability of A happening was 1/6, that's the probability of rolling or picking a 5, times the probability of picking an odd number given that we already picked a 5. So what happens here is then we still have the same probability. So what's going to happen here is that these are then going to be kind of considered independent events. So we're still, because we replaced it, we still have the same probability, right? So my probability of getting an odd, given that I picked a 5 the first time, it doesn't change my result because I replaced it. If I would have held on to my number, then it could have changed my odds of picking an odd number again. But because I replaced it, the probability of getting an odd number is still 1/2. And therefore, they're both the same, and therefore it's independent. So I'm going to be honest with you. What I normally do to kind of determine independent and dependent is I look at the wording of the problem. So again, what I look for is this idea of replacing it, of changing the total number of outcomes. If the person, in our scenario here, if the person picking second has a different pool of values to choose from, then that's a dependent event. If they have the same odds or the same chance as the first person, then that's an independent event. All right, we'll get a little bit more practice with this. Let's go with number 2, which is on page 3. Some more fun examples here. All right, so look, a bag containing some more paper. So we got a bag containing numbers 1 through 6 again. So we'll write those down. A student randomly selects a piece of paper, does not replace it. Okay, there's some keywords there. And randomly selects another piece of paper. Using a sample space to determine whether randomly selecting an even number first and randomly selecting a 4 second are independent events. So randomly selecting an even number, right? Probability of even, there's 1, 2, 3 out of 6, or 1/2. The probability of getting, what does it say? The probability of getting a 4 on the second try, because we didn't replace it, this is going to have a different probability. Because we didn't replace it, this person, whoever picked first, could have picked an even number. And therefore, that would change my odds of picking a 4. Because what if that person picked a 4, right? Then the odds of me picking a 4 are 0%. But if they didn't pick a 4, then I would still have, but they picked a number, I have, maybe 1 out of 5 chance of picking a 4. So let's say this first person picked a 6, right? Then I would still have, the 4 is still available, but now I still change the total number of outcomes. I still have now only 5 choices to choose from, right? Because 6 was already taken. And therefore, it's going to have a different probability than if I replaced it. So again, the keywords here are does not replace And so therefore, this is a not independent or dependent event. We'll just call it not independent is what they kind of are saying here. So a not independent situation. So again, the keywords here are does not replace, because then if we didn't replace it, it changes the overall probability. All right, let's take a look at the next one. So the next one says, using the spinner, find the probability that you will get an even number on your first spin and a number less than 3 on your second spin. So again, if we have to determine, are these independent or dependent events? So because we're not changing the spinner, right? I'm spinning the spinner once. I'm not altering it in any way, right? I'm not like saying, okay, well now no longer 3 exists, and so now you have to spin the spinner, but no one can get a 3 this time. So because I'm not changing the spinner, me spinning on the first try and me spinning on the second try are independent of each other. So this is what we call an independent situation. So find the probability that you even number on your first spin. So the probability of even. So let's see here. We got 2, 4, 6, 8. So out of 8, there are 4 chances. Okay. And the probability of a number less than 3. Well, less than 3 means we don't include 3, right? Because it's not less than or equal to. So I would have to get 2 choices out of 8, which we can reduce to 1/4. So if I want a probability of both of those things happen, this is an independent event. So what I'm going to do is I'm going to use this formula. So I'm going to say the probability of rolling an even number and getting a number less than 3 on 2 different spins is the probability of each event happening separately by multiplying them together. So I would take, probability of both things happening. So A and B is the probability of A times the probability of B. In this case, it's 1/2 times 1/4, which is 1/8. And so we could write that as a percent. A lot of times we write probability as percents, and so we could write it as like 12.5%. All right, let's keep going. Let's do some more math. 9 women and 6 men are on a committee. 2 people are randomly chosen from a committee member to serve as chairperson and a treasurer. Find the probability that both events A and B will occur. So probability of A is, or what A represents is the chairperson is a man, and B is the chairperson is a woman. All right, so again, 2 people are randomly chosen from a committee. So if you're, signing up, let's say you're in a club, right? And you're like, okay, who's gonna be president? Who's gonna be vice president? Who's gonna be treasurer? Who's gonna be secretary, right? So if you're in a room of 9 and 6, that's a total of what, 15 people. Let's say you're in a room with 15 people and someone volunteers to be president, right? And there's nobody else. And so they're like, all right, fine, you have the job. That person then can't be also vice president and treasurer and secretary. And, they can't, then they're off the table. So now we're only down to, for the next vice president role, right? Now we're down to 14 people to choose from. And then the next one, we're down to 13 people to choose from. So my point is that these events, right? The fact that you're choosing people from a committee of 15, 9 women, 6 men, are dependent of each other. And the reason why is because once you pick the first person, it affects the outcome of the second one. And so that's why they're dependent. So we're looking at the probability of A happening. So remember, probability of A is that a chairperson is a man. So there are 6 men on the committee. So that means 6 out of 15. So that means there are 6 men out of a total of 15. So remember, number of favorable outcomes over the total number of outcomes. We can reduce this to 2/5 to make our numbers a little bit easier. Because this is a dependent event, we want the probability of picking a woman second, but given that A has already occurred, given that a man has already been chosen. So because we're looking for the probability of picking a woman, so there are still 9 women to choose from. That didn't change, given that it's already occurred. So because we already picked a man, now we're down to 14 people to choose from. So the probability of B happening, given that A has occurred. So the probability of picking a woman, given that a man has already been chosen, is 9 out of 14. So now we're going to look at our dependent event formula, which is really the same as the independent, just with this slight little change here. We're going to multiply those 2 probabilities together and figure out the overall probability. So again, these are dependent events, which is why we're kind of going this route. So the probability of A and B happening would be 2/5 times 9/14, which is, let's do the math here. Looks like I did my math. All right, so grab my calculator here. So 9 times 2 is 18. Well, actually, let's go ahead and reduce this, right? So let's go this one, this is 7. So I get 9/35. Just that way I don't have to do as much math. All right, so anyway, I'm going to change it into a percent. So if I do 9 divided by 35, I'm going to round my percentages to 1 decimal point. So I'm going to get 25.7%. All right, let's look at the next one. A bag contains 10 red marbles, 5 blue marbles. You select 3 marbles from a bag. What is the probability that all 3 marbles are blue if you A, replace each marble before selecting the next one, or B, do not replace each marble before selecting the next one? Compare the probabilities. All right, so what they're getting at here is independent versus dependent. So if I have 10 red marbles, so 10 red, I like to write down what we have, 5 blue. Okay, great. So that gives me a total of 15. So whenever you're doing a probability, you do need to know the total, right? Because it's always number of favorable outcomes number of total outcomes. So the probability of A, so like we're looking at A, you replace each marble. So this is an independent event. Because we replace them, it does not change the effect or the probability of what happens on the second draw. So you randomly select, or actually 3 draws, right? Second and third draw. What is the probability that all 3 marbles are blue? So the chance or the probability of blue would be there are 5 blue out of 15 total, right? That's the probability of blue. Well, the second time I draw, I still have 5 blue to choose from and 15 total marbles to choose from because, again, we replaced the marble. And on the third draw, same deal. I've got 5 blue to choose from, 15 total marbles. So it might be easier to do this in our heads if we reduce those fractions to 1/3. And so then we get a probability of 1 out of 27. All right, now let's look at the dependent event. So this one says you do not replace. So again, the probability of picking blue on the first draw. Well, because we haven't done anything yet, the probability is 5 out of 15 because there are 5 blue marbles and now total of 15 marbles. All right, so we want 3 blue. So that we have to assume we're looking at the probability of all 3 blue or 3 of the blue being picked. So if one of the blue was being picked in the first try, that means there are 4 left out of 14 total marbles. And on a third one, there would be only 3 blue marbles left because 2 were already chosen out of 13 total marbles. So if we do the math here, I just multiplied across the top, multiplied across the bottom, I get 2/91. So if to compare these percentages, you might want to look at how many times greater one is than the other. So it might helpful, I don't know if you know what these decimals look like. So this is about 0.037, so not a very high probability, and 0.022. So this is like 3.7%. And this is like 2.2%. So the probability of either happening, whether we replace it or not, is actually very, very low. However, there is a slightly higher probability if it's an independent event when you change the probabilities, or when you replace the marble. So what we want to do is figure out how many times greater this is than that. So if I do, how many times greater is this than this, I'm going to divide 0.37 by, so 0.037 divided by 0.022, and I get about, we'll round that to 1.7. So the probability we'll say is 1.7 times greater if you replace the marble. So that's what it means by like kind of comparing the probabilities. You want to know, you found great, but now say something about them. It doesn't have to be, a dissertation here. It just has to be, some sort of comparison statement that talks about like how many times greater one is than the other. All right, we got a couple more to do, and I know that there's a lot, but I want to give you lots of examples because I feel like this unit is a little bit confusing for us. All right, so what we're going to look at now is conditional probability. So when we have conditional probability, let me grab a marker. So it says a quality control inspector checks for defective parts. The table shows the results of the inspector's work. So here's all of our work. Find the probability that a defective part passes. So we want to know the probability of a defective part and that it passes. Okay, so that's kind of like how we write our probability. So sometimes in this case, it'd be easier just to kind of think this one through. So there's the probability of getting a defective part and it passes. So defective and passes is 5, right? So there's 5 favorable outcomes here. So in order for those both things to happen at the same time, to have a defective part that passes is 5. So the probability of just a defective part is 20. There's 29 total, I guess, options, or 29 total values, because there are 29 total. If a part is defective, in our little sample here, we saw out of all the parts there were 29 parts total. 5 of them passed, 24 of them failed. So the probability of being defective and pass, so there's a total of 29. 5 of them meet the criteria. So the probability would be 5 out of 29, which is approximately 17.2%. All right, find the probability that a non-defective part passes. So now we're looking at a non-defective part. So this one has 217 total. So the probability of non-defective and that it passes. So again, how many favorable outcomes do we have? Well, a non-defective part that passes would be 208. So that's the favorable outcomes over the total number of outcomes. Well, the total number of non-defective parts is non-defective parts, I keep saying the wrong word, is 217. So this is going to actually be a pretty high percent. So I got 95.9%. So if the part is non-defective, it has a really high rate of passing the test, the inspector's test. All right, so those weren't really conditional probabilities. What we're looking at now is I'm going to show you kind of a scenario in which we're looking at a conditional probability. So in this one, we're saying at a clothing store, 75% of the customers buy pants. Only 20% of the customers buy pants and a belt. What is the probability that a customer who buys pants also buys a belt? All right, so a conditional probability is, again, the probability of, if we look at kind of what a conditional probability is, kind of going back to what we said at the beginning. The conditional probability is that event B occurs given that event of A has already occurred. So again, it's like one has to depend on the other. Okay, so there's our formula for conditional probability. So we're looking at the probability of buying, so we're getting customers who buy pants and a belt. So the probability of buying or getting a belt, providing that you already bought pants. That's the probability we're looking at. So it says, what is the probability that a customer who buys pants also buys a belt? So buys a belt, given that the customer has already bought, I guess, pants. So let's kind of break down this probability. So the probability of A, so that's the probability of, so if we look at our scenario, this is our conditional probability scenario. So this is when one thing is dependent upon the other. So the probability of A is, so remember, A represents our pants, okay? So the probability of buying pants is 75%. So we'll write that as a decimal, 0.75. The probability of B, we don't really know. That's the belt. So we know what the probability of buying just pants are. We know probability, we said 20% of the customers buy pants and a belt. So that's the probability of A and B. So pants and a belt. So this represents pants and a belt. So this is 20% or 0.20. And then we also are trying to look for the probability of B given that A has already occurred. So again, what this means in words is your probability of getting a belt given that people already bought pants. Okay, so that's what we're looking for. So our conditional probability looks something like this. So we're looking at the probability of both things happen at the same time. So this would be 20% out of the probability that A occurred first. So the probability of getting or buying pants first. So all we're looking for here is 0.20, which is the probability of both, divided by 0.75, which is the probability of buying pants. Together, that would give me approximately 26.7%. So that's what conditional probability would look like, okay? So it's the probability of something happening given that something else has already occurred. All right, strongly encourage you guys to practice some of this stuff and obviously come to class with questions. We'll do a little bit more in class as well, but it's always helpful to kind of try some on your own. All right, that's it for now. Bye.